Welcome to the CSEC Physics Crash Course video. I'm Mark, and let's get started. Today, we're going to see what we're going for Hooke's law. So what exactly is Hooke's law? The precise definition is the strain in a solid is proportional to the applied stress within the elastic limit of that solid. In English, it means that materials or things stretch in proportion to the amount of force that's applied. And to be clear, within the elastic region, the linear portion, or the linear elastic region. Now, what we're really getting at is the fact that when we stretch something, how much it stretches is quite literally in line with the force we apply. In other words, the more force I apply, the more it stretches, vice versa. Alright, so a quick note before we continue. We need to establish what exactly is elasticity and plasticity. So elasticity quite literally describes, a material's ability to return to its original shape after it's deformed or a force is applied, what have you. So elastic materials, those are materials that, return to the shape after you stretch them, you pull on them, you slap them, you squeeze them, whatever. So if you think about like rubber bands, after you stretch them, balloons when you let out the air, springs, plate, springs, things that go back to the original shape, gelatin in some cases, those are elastic things. Plastic things now, or plasticity, is when after you apply these forces and loads, these deformations, they don't go back to the original shape. So quite literally everything we call a plastic, they are plastic because we call them plastics because they undergo plastic deformation. Play-Doh, worn out springs, metal, when you bend them, those undergo plastic deformation. Alright, so in the top left corner, you'll see an elastic material. You apply a force by stretching it, you remove the force, letting it go, it goes back to its original shape. In the bottom right, you will see metals undergoing plastic deformation, where these presses are applying a force and the material shape permanently changes once the force is removed. So this behavior can be tracked using a force extension graph, and what a force extension graph simply shows is, how much the object, or say a spring, length changes or deforms in accordance to a particular force, vice versa. So if you have y force, it's going to correspond to an extension of x distance. What we're interested in here is actually the linear section of this purple shaded area. The purple region being the elastic region, so any force or extension within this area will return to its original shape. Once you pass point B, then you will go into the plastic region and you will no longer be able to return to your original shape once you pass point B. You notice here in this graph, you have the proportionality limit at A, and then there's a slight curve to B. What that simply means is that after point A, no longer is the extension directly proportional. You start to get some variation where the amount of force you apply might lead to less and less extension, or more, vice versa. Different materials have different graphs, but overall you can track this behavior. Alright, so back to Hooke and springs. So we established that the strength of a force affects the amount of deformation, or the change in length, in a proportional manner. Alright, that makes sense. So what exactly did Robert Hooke contribute? But in simple terms, really and truly, he just figured out by how much different materials did this. And he described it by the formula F is equal to negative kx, where F is the force, K is the spring constant, and X is the extension of the spring. A key thing to keep in mind is that the negative sign in this equation is just customary in describing the restoring force. So the restoring force, I'm supposed to know about this, but as a reminder, it's you know, every action has an equal and opposite reaction, right? So when you pull down on the string, there's a force that wants to go back to the equilibrium position. So that's the restoring force. You sit down on a chair, the chair applies a force back to you as well. That's the restoring force. So whenever you use the negative sign is whenever you're talking about the restoring force. Otherwise, you don't need to put it. But this is how it's represented customarily. All right, so speaking a bit more on the spring constant, really and truly, all the spring constant does is tell us how stiff a spring is. If you have a high K value, then it means you have a stiff spring. If you have a low K value, it means you have a softer spring. In the GIF, you have two cars, equal mass, so, gravity is the same in this area, so they both apply the same force. But you notice that the one with the low K value is a lot more bouncy and wobbly, the one with the high K value, firm up on thing. Alright, so you do your lab or you get a data sheet for a spring, and you're looking at your force extension graph. You might be curious as to what really are going for the linear section. Well, an interesting observation is that the gradient of that linear line, is actually the K factor, the spring constant. And if you're wondering why is that, you can just take a look at the equation again. F is equal to Kx. And if you really meds the formula, you realize that it's in the form y is equal to mx. You can say plus c, but in this case c is 0 because that's the y-intercept where it cuts the y-axis. So in this case you can say that c is 0. So we'll just leave it out and say y is equal to mx. Now another way to look at it actually is as a ratio, one quantity to another quantity, y to x, force to extension. So if you say, all right, if you transpose this equation, you'll get the format k is equal to force over extension. If you look at it graphically and you want to pose it that way, you can say force is over extension same way. But if you think about the force constant or the spring constant as a ratio, it makes sense. Like, how much force do I need to apply in order to get a certain amount of extension? That is what the K factor really tells us. How much force do I need to apply in order to get a certain extension, vice versa. If I extend the spring by this much, how much force do I, will it take in order to do that? And that's really and truly what the K factor is all about. Before we get into any calculations, it's worthwhile to think about some applications, because physics, describes the physical realm, the physical reality. So try not to get caught up in the whole, theory right off the bat. So the simplest application of springs and where you might find hooks in place is spring balance. And how those work is that the K factor of the spring, so the amount of extension you get from a certain load. So all the simple is just put that together and the mark off the tube or the ruler, whatever it is, and you have your spring balance. Springs are in vehicle suspensions, they're in camera sliders, they're in pens, trampolines. Springs are everywhere. So my challenge to you is to look around, see what kind of mechanisms have springs in them, and try to guess or think about how you would test figuring out what their K factor would be, or how much force they need to extend and retract. So let's put Hooke's law to use. So this question says a spring has a length of 50 centimeters normally. When a 5 Newton load is applied, it stretches by 10 centimeters. Determine A, the spring constant, and B, the load which will stretch it to 75 centimeters. So with all physics problems, before you do any calculations or anything, just establish what was given. So you have a spring that is 50 centimeters normally. Always work in your standard unit, so we're going to change this to meters, so that would be 5 meters, and that's it when there is no load. So this is no load. When a 5 Newton load is applied, it stretches by 10 centimeters. So we have another spring, or the same spring, and give it another curl. You know, a load is applied, so there's a box attached, and it has a 5 Newton load, and it increases by 10 centimeters. So this is 0.6 meters. Now, the final thing to consider is that, all right, Hooke's law applies. It's within its elastic region. So we can state our formula to be F is equal to Kx. Now, looking at A, in order to determine the spring constant, we look at what we have written down. You could look at it to say, all right, the spring constant, you may know the units to be newtons per meters, or you may look at what you have, what they give you. You know, you're looking at the formula, and you'd probably transpose it to say, all right, K is equal to F over X. So you look at what they give you, look where you have any forces, and then your associated lengths. And in this scenario, we see that we have a 5 Newton load and a 0.6 meter extension. But it's important to keep in mind that this X here is actually the distance that it changes. So you can look at this as delta X, you know, the change in distance. So K is equal to the force, which we know is 5 newtons, divided by the change in X, which is 0.6 minus 0.5, which is 0.1 meters, which will give us a K value of 50 newtons per meter. And this is our spring constant. Now for B, they want us to find the load, which will stretch it to 75 centimeters. And many CSEC questions, the flow of the questions are that they'll ask you the most basic thing first, and then you use the answer from the first part to answer the second part. So you want to find the load, which will stretch it to 75 centimeters. Now, for me, I'd work with, all right, I have a new distance, so we need to start from a new baseline now. So B is really asking, all right, or is really saying, all right, we have a spring, we stretch it, you know, this distance is now 0.75 meters, you know, what's the load? That is what B is asking. And similarly to how we found the delta X for A, you know, said, all right, the baseline is 0.5, the new distance is 0.75. So X will be equal to 0.75 minus 0.5, which will give us a distance of 0.25 meters, 25 centimeters. So it stretches by 25 centimeters in scenario B. Now, in order to find the force or the load, it's just simply substitution, where force is equal to Kx, where K, we found out from the previous question, part A, we found K to be 50, and we just multiply that by X, which we just found to be 0.25 meters. And therefore, our force is 12.5 newtons. That is B. So it takes 12.5 newtons in order to stretch it by, or stretch it to, 75 centimeters. So for our second example, the question asks, or the question states, an unloaded pickup truck sits 0.8 meters above the ground. What's the maximum load? In this case, we really want the mass. Remember that you can use the loads to determine your mass. The truck can carry in order to clear a speed bump with a height of 0.2 meters. The combined K factor of all the springs within the vehicles is 5 times 10 to the 4 Newton meters. You know, this pickup truck has 4 springs. When springs are in parallel, they distribute the load, but in this case, they're identical, and it's very simplified. So we're going to treat it when springs are in parallel. You can treat it as one combined, just one big spring, pretty much, basically. So again, you know, state what's given, visualize. In this instance, I don't know if I can draw a pickup truck, honestly. It would be much better on pen and paper. But say you have, you know, this being the rear side of the pickup truck. So this is a wheel. This is a wheel. This is the ground. We can say that this distance here, from here to here, is 0.8. And you know, in the second scenario, we want to find the maximum load, so we know that the new distance will be right here. This distance, you know, the truck is going to squat, and it's going to be 0.2 meters. So we want to find the maximum load, and they also gave us the K factor, so we know that K is equal to 5 times 10 to the 4th Newton per meter. Now we state Hooke's law. Hooke's law's formula is F is equal to Kx. We have our K. We'll get the mass, you know, we get the load or the mass from force. So we need to find our X. And how do we get the X? You know, X is equal to 0.8 minus 0.2, and that gives us 0.6. So the overall truck is going to squat by 0.6 meters. And after this, it's just simple substitution. F is equal to 0.6 times 5 times 10 to the 4. Multiply in a calculator, you get 30,000 newtons. Now, this is the actual load, 30,000 newtons, but in this case, we want the mass. So we just take it one step further, and we will have, we remember or recall that force is equal to mass times acceleration. We have 30 kilonewtons over here. You know, we don't know the mass, but we do know that acceleration due to gravity, at least in CSEC's case, is 10 meters per second. You know, 9.81 is more accurate, but I think CSEC uses 10. In order to find the mass, it's just a matter of transposing. So M is equal to force over acceleration. And you carry this under here. So what that looks like is M is equal to 30 kilonewtons divided by 10 meters per second squared, which leaves us with a mass of 3,000 kilograms, or 3 metric tons, which is pretty, it's a lot. So it's a pretty hefty truck. And yeah, that is the answer. So again, you know, that's pretty much Hooke's law. It's within the elastic limit. That's pretty much it. So again, for this question, they gave us the K factor, the spring constant. You know, they told us the distance that the spring traveled by saying, it's gonna squat to a height of 0.2. So you find the total distance or the difference, and that leads us to 0.6. It's just a simple substitution. 0.6 times K, that's 30,000 newtons. And then in order to find the mass, we recall that force is equal to mass times acceleration. And, we'll do a transposition and we get our 3,000 kilograms or 3 metric tons. So in summary, materials that stretch in proportion to the applied force up to the proportionality limit obey Hooke's law. That's a linear section on the graph. Materials that return to the original shape or length after the force has been removed are called elastic. The ones that do not are called plastics. The spring constant tells us how stiff or soft a spring is. The gradient of the linear portion on the force extension graph is the spring constant, and Hooke's law is represented by force, or F is equal to negative kx, keeping in mind that the negative sign just represents the direction that the force is being applied.